Are you recording this?
All right, what I have here, guys, is a very short section of the DNA. It's been flattened so that we can simplify things a lot, but I want you guys to see a couple things about the model that I'm using. Number one, we have 3 components to our nucleotide. This part right up here represents the phosphate, okay? So to kind of orient you a little bit. What would this portion of the molecule be if it's adjacent to the phosphate?
Sugar.
That's our sugar. If this is DNA, what kind of sugar is it?
Deoxyribose.
Very good, deoxyribose. That means that this is our 3rd component, which would be
Base.
the base, our nitrogen base. You guys might also remember that you can number the carbons to help you determine the top and the bottom. Since this is a phosphate, what carbon number would this one be right here? Not number 1. It's actually 5. It's 5 because we go 5, 4, 3, 2, 1, and then 0 is at the top. The shape's a little bit different than we've been using, but if you can remember that 5 is next to the phosphate and 3 is at the bottom, that's the most important thing. This is going to help you guys see that we have 2 strands that are going in opposite directions. Notice that the phosphate is on top on this side, but the phosphate on this strand is completely facing the other direction. Do you remember the name for the 2 strands that go in opposite direction? We kind of have a name for that orientation where they go equal but opposite. Remember, I jokingly called it a political party?
Anti-parallel.
Anti-parallel, very good. So you can see that they do go in opposite directions. The code on this side would be read in the opposite direction from this side, okay? So we've got our parental DNA because this represents the original copy. Now, we read yesterday about something called semi-conservative replication. If I call someone a conservative today, it's kind of a politically charged thing. But in general, what does it mean if somebody's conservative?
Don't like change.
We don't like change. I think that's short and sweet, and it's great. If it's semi-conservative, what does the prefix semi do to that word? It means half. Very good. So we are dealing with something that's half old and half new. We're going to use the 2 strands as our templates, our originals, and we're going to base our copy off of those. So I need to use these as a template, but I need to separate them a bit. So I'm going to use an enzyme called helicase. And like a zipper, you can see it's wedging its way down. What kind of bond is being broken when we separate those 2 nitrogen bases from one another? It's the weaker of the 2, it's the hydrogen bond. Very good. So if you guys can imagine, it's like pulling apart 2 pieces of Velcro. But if you're not careful, those 2 pieces of Velcro can go back together, right? So we need something to hold them apart. I'm going to need a single-stranded binding protein. Okay, so they are going to hold these 2 strands apart from one another. I jokingly call these my best friend proteins because, like your best friend, they would keep you from getting back together with your ex in case it was a bad move, right? So they say, no man, don't do it. This is a bad move. So they
choke you really quick.
They choke you, right? Whatever it takes, right? This is your best friend. So these single-stranded binding proteins are keeping the complementary strands from reconnecting or re-annealing. That's the technical term for it. That means that they'll stay open and the replication bubble will stay separated. Now realize that this is one end of a separation bubble. So there's another helicase going in the opposite direction. But we won't do all that at once. Let's pretend that we've kind of had the entire bubble unzipped. Okay. Normal DNA wouldn't separate like mine are. What kind of bond would hold those nucleotides together so that I have a nice strong backbone? Those are our covalent bonds. Very good. So the sugar phosphate bond is a nice strong covalent bond. The weaker hydrogen bonds are meant to be unzipped. Now that I've got the 2 templates kind of opened up, I'm ready to start my copying. But I can't just add DNA bases. Kind of like a wall that you might have put up after some construction work. Maybe it's brand new drywall. You've patched all the holes, ready to put on some color. What has to happen to that wall before you can actually put some paint on the wall? Ooh, good. Primer. We need some primer. So I need an enzyme that can start the process. So I'm going to use RNA primase to actually lay down some nucleotides that I can use as the basis for an attachment. So I'm going to start by putting some nucleotides. This one is RNA, because it's RNA primase. So is this one. Now this is kind of symbolic of maybe 5 or 6 RNA nucleotides. RNA primase is special. It doesn't need to have a pre-existing nucleotide to attach to. It can make this kind of wobbly connection between this nucleotide and the RNA primer, even though it's only a hydrogen bond. And that's critical because DNA polymerase can't make that connection. It needs something already there to attach to. So now that we've got our primer, I want you guys to notice something. This strand and this strand are being replicated on opposite ends of the open bubble. And when I start to paint in using DNA polymerase, this enzyme, DNA polymerase 3, is going to start adding nucleotides. You saw this on the video. The 5' end of the new nucleotide is attached to the 3' end of the old nucleotide. This is why the book refers to it as a 5' to 3' direction. The new attaches to the bottom of the old. Okay, so you can imagine that this is following right behind the helicase, and we're adding in new nucleotides. Similar, we're going to have the same process going on the other strand. You guys will notice that I've kind of made my life easy, and I've made all of these nucleotides identical, although that would not be the case if this were the real code. This enzyme is going to move down and create covalent bonds to the 3' end of the previous nucleotide and hydrogen bonds to the nucleotide's nitrogen base that's next to it. Okay? I want you guys to imagine, though, that you're watching this helicase. From your perspective, it's going towards the camera, right? We're going towards Z. So the bubble's opening and expanding that direction. Which of these two sides is going to continue to synthesize new DNA right behind the unzipping process? This one right here? You're right. Okay. Can you guys imagine as we unzip towards this end, we just keep on opening up more template DNA, and we can just keep on adding in more bases. This side is being replicated in the other direction. That whole anti-parallel thing is happening. So we're replicating DNA just like the other one, but now we've got a dilemma. I finished this section, and now if you can imagine, to our side over this way, we now have more DNA that needs to be replicated as well. But the enzyme's going this way. So at a certain point, the enzyme's going to have to retrace its steps, go towards that end, and then fill in the gap. And then when it's done with that, we've opened up more DNA. So it's going to have to retrace its steps again, and then fill in the gap. I liken this to somebody walking down the hall with muddy shoes. And the janitor sees them about midway and takes out the mop, kind of grumbles under their breath, and starts kind of mopping up those muddy footprints. But the janitor is going the opposite direction because they want to clean up the footprints that have been laid down by the mud. So they've got all the footprints cleaned up. They can see where they started coming in through the door, and then turn around. Oh no, that section that was clean before has now been walked over. And now I have to retrace my steps and go mop up that other section. So we're constantly playing catch up. Every time we think we've finished a section, another section's been opened up. Out of these two strands, which one do you think is going to be the most efficient and having the least wait time? Everybody seems to be pointing to this one? Okay, great. This is called the leading strand because it's going to follow right behind the helicase, and it's going to allow it to do one continuous replication within this bubble. This strand, however, isn't so lucky. It's got these stops and starts, so it's going to have what we call a lagging strand synthesis because it's falling behind. It also leads to one of my favorite terms of the chapter called Okazaki fragments. Okay, an Okazaki fragment is what we call it from one primer to the next. It's the segment of DNA that's been replicated in one stretch. Which strand would have more Okazaki fragments? This strand or this strand? On your left, very good. So this would be the lagging strand. It's going to have more fragments. Now, reality check here, guys. If this is a bubble and it's enlarging in both directions, can you guys see how in some areas this strand will be leading but there's a helicase going in that direction as well. So for some of the bubble that we've opened up, this strand will also be lagging behind because the helicase that goes that way will be going in the opposite direction of these enzymes. So there's no such thing as a true leading strand or a lagging strand. It might be better to think of it as this segment has a leading portion and a lagging portion. Can you guys see why it's much more efficient to replicate in small segments and then join them all together than it would be to start on one end of the DNA or the chromosome and go all the way down? It would just take forever. We've got 1 trillion bases to add in. So we have these multiple bubbles. In between the fragments, in between the Okazaki fragments, we eventually have to come through and we are going to replace this RNA primer with DNA. Because, well, RNA isn't the actual code, right? If this were an adenine in DNA language, what should pair up with it in DNA language? A thymine, a T. But if this were an RNA primer, what letter would I have instead? I'd have U for uracil. So that's got to be fixed. I've got to replace it. So my DNA polymerase number 1 comes through and clips it out and replaces it with a DNA version. But now we have this weird bond that was formed. Remember the enzyme adds the 5' to the 3'? Well, we added a 3' to a 5'. In other words, this bond is not actually formed yet. So we have a gluing enzyme right there, okay? It's going to actually fill in that gap with a covalent bond. This enzyme is called DNA ligase. To ligate means to glue or fuse things together. Once DNA ligase has joined those, we now have a replica of what was originally attached to this original. So it's semi-conservative. We've got half old, half new, and we've got 2 exact copies. All right. Thanks, Aid.